So here we have a power supply unit. Here's the transformer, here's a single diode, and this is the light bulb that we'll be using as a load. The light bulb is going to use the electricity that the power supply unit provides. Having only one diode, however, this is known as a half wave rectifying power supply unit. So let's turn some power on and see what happens, shall we? Get the plug first and plug it in, which is always useful, and then so we've got mains electricity coming in here, a lower voltage coming out, being rectified by the diode, and the bulb is illuminated. Well, that's all very good, but let's see if we can understand a little more of what's actually going on. So first of all, let's measure the voltage coming into the transformer. Better make sure it's on the right scale. And it's 244 volts of AC. 244 volts of AC going into the transformer. How much is coming out? Well, we'll change the scale again and then measure it. There's 3.8 volts of AC coming out. So let's see how much voltage is going to the bulb, because that will be DC. So we'll just measure the voltage across the bulb, and we find it's 1.28. It was 3 volts something going in AC, and only 1.2, 1.3 at most, coming out. What's going on there? Well, things, as they say in Alice in Wonderland, get curiouser and curiouser if we add a capacitor to the situation. I'm going to put this capacitor, these wires, across the bulb in parallel with the bulb, and let's see what happens to the brightness of the bulb. Oh, it gets much brighter. Take the capacitor away, it gets dimmer. Put it there, it gets much brighter. What's happening? Well, let's take a reading on the multimeter and see. So we'll put the probes, and if I can hold this all together with just 2 hands, that will be advantageous. And we'll take the wire away from the gauge. So we've got 1.28 volts going in, but if I put the capacitor across the bulb, that jumps up, well, it did anyway, to 3.4 volts. Take the capacitor away, 1.28, put the capacitor in parallel with the load, with the bulb, 3.43. What on earth is going on here? Well, it would be very useful, wouldn't it, if we could actually see the electricity going through the various wires. You can't actually see the electricity, but there is a device that will help sort of paint a picture of what the electricity is doing as it's going from the transformer to the load, in this case a light bulb. That device is called an oscilloscope. And to understand a little bit about oscilloscopes, there now follows a crash course on the basic principle of an oscilloscope. Don't go away. By moving a magnetic field side to side through the coil, it induces an electric current in that coil and is displayed by the meter. Whichever direction I move the magnetic field, left or right, the electric current flows in the same direction. If I stop moving the magnetic field, the electric current stops. This is a different type of meter. It's called an oscilloscope, and it's kind of drawing a picture of you, for you I should say, picture of you, in much the same way as the meter needle went from side to side when I moved the magnet through the coil. Whoops. So does the trace on this oscilloscope move from left to right and right to left as I move the magnet through the coil. This is a rather inconvenient way of looking at an oscilloscope though. So let's turn the oscilloscope the normal way round. It's more usual for an oscilloscope to be viewed like this, where the peaks of the voltage that are produced are in the vertical sense. It's also rather inconvenient to keep sitting here moving this magnet in and out, so I think we'll have a slight change. But just bear in mind that when the trace goes up and down, when you see the up and down movements, it simply means that it's an alternating current, just as we saw when the oscilloscope was on its side. Well, now we can see much the same sort of image. It's a waveform, sinusoidal waveform. But let's just remember that when these loops, these peaks, are above the centre line, it means that the electricity is simply travelling in one direction, in that direction. And when these peaks are on the underside of the centre line, it means the electricity is simply travelling in the opposite direction. So one's going in one direction, the other half is going in the other direction. So here we can see the setup that we had before, except that I put a protective case over the transformer because it had some rather lethal voltages running around it, the 240 volts mains, and I have a particular aversity about receiving lethal electric shocks. But what we've got here is the oscilloscope probe, and it's connected to the alternating part of the circuit, the AC part of the circuit. And we can see that waveform, this sine wave or sinusoidal waveform, remembering that the top half of the waveform means the electricity is travelling in one direction, and the lower parts of the waveform mean it's travelling in the opposite direction. And it's changing direction, as we can see here, 50 times a second. Okay. What does the oscilloscope tell us about the waveform that we see after the diode? Well, we just changed the position of the probe, and now we see a very different waveform. This thick blue line going through the middle of the screen represents 0 volts. 0 volts. And we can see that we're getting periods of time when there are indeed 0 volts going to the bulb. These peaks are direct current. It's called pulse direct current. We're getting pulses of the current travelling in one direction. But there are times when you would normally have the lower loops of the sine wave, which don't exist at all now because the diode isn't switched on. It's switched off when the electricity is trying to flow in that direction. So the electricity getting to the bulb after the diode is getting, you can think of it as like machine gun bullets coming out of the barrel of a gun. It's a series of pulses, as though someone were using a battery but turning the battery on and off, on and off, on and off, on and off, 50 or 49, between 49 and 50 times a second. And that's the reason why the bulb doesn't burn very brightly. And if we put the multimeter on it, we can see that the voltage is only relatively low, 1.78 volts. It's the nature of these multimeters that they take an average voltage that's being received, at this case, at the bulb. So although the actual voltage is rather more than 1.78, the average, because there's a period of time when no voltage is being received at all, is only what we just saw, 1.78, I think. We can't see the bulb flashing on and off because our eyes can't respond that quickly 50 times a second is much too fast. We simply see the bulb as burning relatively dimly. Okay, but that was only part of the story, wasn't it? What happens when we apply a capacitor in parallel with the load? Well, let's do it now. Let's see what happens to the bulb. Oh, much brighter, much brighter. Disconnect the capacitor, the bulb goes dimmer. Connect the capacitor, and the bulb becomes brighter. Where's that extra electricity coming from to make the bulb so bright? Well, to some extent, we can see the answer on the screen. Let's freeze that image. Now we can see that the voltage at no time is dropping down to zero. There's the zero line, that thick blue line in the middle of the screen. It's staying way above that. How is that happening? Well, the best way to describe it or to demonstrate it is to actually use a whiteboard. So that's what's coming up next.